Okay, 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 fine. Okay. So now coming to whatever the topic for this session is data generation and model fitting using popular discrete and continuous distribution using R. So mainly coming to this part, the data generation. Actually, the data generation means whenever there is a random experiment is going on and there will be some outcome of that experiment, okay, that we call it as a sample space. So let me give a brief background of what I am going to discuss in this session, and then we shall go the further one by one by using R. Okay. Now coming to before going to this data and whatever is statistical data, first we have to understand what do you mean by a random variable. A random variable means I'm not going with a very rigorous definition of the random variable, which is quite difficult, and also it is outside the scope of this whatever the workshop is considered. Totally, I am not including any theoretical aspects in this concern. Just I am giving you what is simply a random variable. A random variable is nothing but it is a set function which is defined from a class of sets to the real line. Okay, so that's why it is called as a set function. Usually, random variables are denoted by the capital letters. Now, for a layman, if I wanted to tell what do you mean by the random variable, suppose there is a experiment is going on or which is conducted. Say, for example, tossing a coin. This is one of the very simple example which we start to understand the concept of random variable. Once if you know what you mean by the random variable, sample space, all the things, then I will talk about the data generation and the different distributions which are available in statistics, discrete as well as continuous. Now coming to this, the very simple experiment is tossing a coin or rolling a die. Sorry, there is a typo off is there that I have to remove. Okay, rolling a die. So if you consider these two experiments, these are some random experiments we are going to conduct, and whatever the outcome is going to be there, that is going to be a random. If I toss a coin, I may get head or tail, which is denoted in the all possible outcomes are either it's going to be a head or tail putting together. This is called the sample space, which we denoted by the set. Okay. So whenever there is a random experiment, we don't know what is the outcome we are going to get, which is going to be purely a random. That time, but I know what is the all possible outcomes of that experiment. If I list all the outcomes of that random experiment, we call that collection as a sample space, which is denoted by capital letters. Again, here S1 is one random sample, one random sample space for the first experiment tossing a coin. That is, all possible outcomes are head and tail. Similarly, if I roll a die, I'm going to get one, two, three. These are the face values of a die. So the collection of all these things, which we call it as a sample space. Now, what we are going to try to do here is, whenever I define a random variable means what here? This is a very simple experiment, which I am going to discuss. Now, if I toss two coins simultaneously or three coins simultaneously, that time I'm going to get all, if I list all the possible outcomes, okay, like if I throw a two coins simultaneously, I'll get head head. In both the coins I'll get head head, head tail, th, like that I can list out all possible outcomes. Now what happens is, in these outcomes whatever I am going to get, which we call it as an event, now I am interested how many heads I am going to get. That means my random variable will be taking the values that how many heads I am going to get. There are four possible outcomes if I toss a two coins. Head head, HT, TH, that is first coin is tail and second coin is head, and both are going to be tail. If I count the number of heads, then my random variable is number of heads I'm going to get while tossing a two coins. So the possible values that I'm going to get for my random variable is 2, 1 and 0. Forget about the events. THHT both will yield 1, and the last one is 0. That is, if both the outcomes are tail, that time number of heads will be 0. So my random variable will be taking the values 2, 1, 0, because my random variable is number of heads. So similarly, if you take a 2 dice, then you can list out all 36 pairs, 1, 1, 1, 2. Then you can talk of your random variable as sum of whatever the outcomes are going to come. Okay, so like that, there are the definition of random variable will go like this. Okay, coming to this last point, in each of these examples we are interested in numbers that are associated with the outcome of chance experiments. Chance experiments means that's a random which has, that is, the values taken is represented by the random variable. So this is how we define random. Why do we define random variable? Means with associated with all this, whatever the outcomes we are going to get, we are going to assign some probability of that. Means what's the chance that is going to occur. So hence I'm not going very rigorous with all these things, because I have to cover little bit more about the statistical distributions. Okay, just this is a brief idea I'm giving you. You can refer any standard books, you will get all the definition and examples related to this. Yeah. Coming to this is one of the example which I was discussing about a coin tossing experiment. If a balanced coin is tossed 4 times, then we have the following. So if you look into the first column, these are all possible outcomes we are going to get if I toss 4 times. Then each of this is going to be a balanced. So the occurrence of each of this having the same probability, that is 1 by 16. Now coming to how many heads, because my random variable here small x denotes the value taken by the random variable capital X. Here each is going to be 4, 3, 3, and so on. You can observe the number of heads and the whatever the things are going to come. Coming to this last one, all are TT, which is going to be 0. So this is one simple way of defining the random variable. Now we are going to talk about the probability measure on this one. Again, that is also one of the theoretical concept which I am not going to be concentrating much on this one. Now we shall talk about, as the title itself is data generation and model fitting using popular discrete and continuous distribution. I will talk a little bit about this discrete distribution and continuous distributions, and then I will talk about how to generate the observations from that distribution and how to fit a model. Okay, how to fit the model for the given data. Okay, now coming to this one, uh, there are some standard discrete distributions are there. Coming to this, first of all, I have to define what do you mean by a discrete distribution and what do you mean by a continuous distribution. First, I will talk about the discrete distribution. So, generally, whenever we talk about the discrete distribution, means there is a random variable which follows some distribution. If I call that distribution is going to be a discrete, means that random variable will take finitely many values or countable. So more precisely, what we are trying to say is, if my random variable x is going to be a discrete one, if it takes finitely many values or countable. Countable, I will come into the last two distributions. Coming to the finite thing, now what happens here is, so this is a discrete uniform. The very basic distribution that we are going to have is a discrete uniform. Okay, so here this omega whatever is there, the notation that is written here, so this is again, this corresponds to the sample space. Now there is a sample space. Okay, in each of this, whatever the values are there in this sample space, if there are n values or n observations are there in this set, the sample space, for each of that value whatever is there, we call it as an elementary event, and for each I'm going to assign the occurrence of the probability is 1 by n. So coming to this earlier case, okay, If you consider this S2 means this is a sample space which I have got it as upon rolling a die. So the possible outcomes are 1, 2, 3, 4, 5, and 6. Each of these values inside this, whatever the set is there, they are called the elementary events. And for each of these elementary events, if I have the probability of occurrence is going to be equally likely. That means the probability of occurring 1 and the probability of occurring 2, 3, 4, each one has an equal chance. That is, totally there are 6 outcomes are there, and each one having a probability of 1 by 6. So this, in this way, for each elementary event, if they are going to be equally likely the occurrence, then we are going to have the same probability. Even in the first case, head and tail, probability of getting head or probability of getting tail is going to be half. That is equally likely. So hence, the first distribution which we are going to consider is discrete uniform. Means whatever the values are there, it is going to have the equal chance. Okay, and the second one is actually it is a Bernoulli distribution, because more generally we are going to talk about the binomial. Okay, if the Bernoulli, whatever we have, if my random variable takes either 0 and 1, now what happened to this corresponding to S1? So suppose if I code this as h is going to be 1 and t is going to be 0. That means my random variable will take either 0 or 1. That is number of heads. Okay. If any discrete distribution, it takes 0 or 1 case, okay, where 1 is a success and 0 is going to be the failure, then that will constitute the Bernoulli random variable or Bernoulli distribution. It follows Bernoulli distribution. Having the probability is equal to P. P stands for probability of success. In this case, equally likely means I will say half half. So P will be equal to half, but in general I can say probability of occurring head is going to be P and probability of getting tail is going to be the complement of that. That will be 1 minus P. Putting together, altogether it's going to be a probability mass function. So whenever I talk about a discrete distribution, always I'm going to talk about a probability mass function. Now what do you mean by probability mass function? Let us see. So this is the basic definition of probability mass function. Suppose we have a omega, there is a sample space and we have all those events, that is x. If I get probability of my random variable equal to some specified value of x or small x, okay, which is denoted by p of x, okay. If this p of x summation over all x, probability of x equal to 1, if this is equal to 1, we say that this p of x is going to be the probability mass function. Means I am going to put some mass on each of the values x1, x2, xk, if there are k values or n values, whatever is there. On each of these small x, we are going to put some mass. That will be the probability, so that the total probability will be equal to 1. If this condition is satisfied, then we say that p of x, whatever small p of x is there, it's going to be the probability mass function. So whenever if there is a discrete, again I am repeating, so discrete distribution means a random variable which takes finitely many values or countable. Okay, the basic is Bernoulli distribution. Its generalization is going to be binomial. Means if the experiment, the coin tossing experiment, as I told you, if it repeated n times, then that is going to constitute the binomial distribution. And the PMF of binomial distribution is going to be ncx p to the power of x 1 minus p to the power of n minus x, where the small x takes a value 0, there is no success at all, there is 1, there is totally n. That means the coin tossing experiment, whatever the Bernoulli random variable which I told, if it is repeated n times, and if I take the number of heads or number of success, whatever is there, so here p stands for the probability of success. If it is repeated n times, then I'm going to get ncx p to the power of x, 1 minus p to the power of n minus x, where x takes the value 0, 1 up to n, and this probability of success always lies between 0 to 1 and 0 otherwise. Okay, so this is one of the very basic definition for the binomial distribution. So this is one of the discrete distribution which one should know. These are some fundamental things. I'm not covering all the discrete distributions. Some standard I'm going to talk. Now coming to this second one is going to be the Poisson distribution. So this is one of the distribution which we use to model the rare events. So let me repeat this one. One of the application of this Poisson distribution is you can find whenever there is a data related to earthquake. In many other places, thanks in India, we are not having that problem. But in many countries, always whenever they wanted to buy a land or whenever they wanted to build a plot, okay, whatever the house is also considered, they always try to see that what is the chance that the earthquake is going to happen or some natural uh, disaster, whatever is going to happen. So such kind of data is also available in many places in US, and they are modeling that data using this Poisson distribution. So this Poisson distribution is used to model the rare events. Okay, and there are some very good standard examples are available in many standard books. They have given a lot of examples related to this one. So if you want to study more regarding this one can refer that. Okay. So I'll be updating the reference also in my presentation that I'll be sending to madam. Madam is going to circulate to all of you. I will type more material regarding this one. I will include that one in my write-up and I will share with you. Okay. Now coming to the next one is going to be the geometric distribution. Okay. So the geometric distribution and its PMF is given by P of x is equal to P into Q to the power of x. So this distribution is used whenever we are going to see what is the probability that we are going, the first success is going to occur. Means already there are, if there is a some k things has happened, k minus 1 already failures have occurred and kth is going to be the success. And then it's first time we are going to get a success. That is what to model such kind of data we use this geometric distribution. So it enjoys certain properties also, these distributions. They are quite standard and in many places it has a lot of application. Geometric distribution, it is a discrete version of the continuous distribution we call exponential, which is used to model the lifetime data. So this is a discrete version of this, and these two distribution enjoy the property of lack of memory. So because of this reason, the discrete version is geometric distribution, and many applications regarding the lifetime of a components or whatever related to that one means lifetime data. We use the discrete version is geometric, and its analog to that one continuous is exponential distribution, which I'll be talking in the next. So now coming to this one, we have discrete distribution. So I'll be taking a discrete uniform, I'm not going to consider here. But coming to binomial, Poisson and geometric, I'm going to explain how the PMF will look, how to plot the PMF, and also how to generate the observations from those distributions. Okay, that I'm going to talk in the next. Now coming to this one, continuous distributions. Now already I told discrete distribution means it will take the values either finitely many or countable. Now coming to this one, this sort of distributions means a random variable which will take the values over the interval or which will take the infinitely many values. Okay. So there are some standard distribution regarding this one or a continuous distribution. So whenever we talk of a random variable which is going to be continuous, or in fact more precisely it is called absolutely continuous, okay, then there will be associated function, we call it as a probability density function. So we are going to plot the PMF and PDF for all the distributions which we are going to discuss. Okay. So what do you mean by a probability density function? a non-negative real valued function f of x, small f of x, a non-negative real valued function small f of x is called PDF if it satisfies this condition. Remember, this is a real valued function, non-negative function. If the total integral over the entire range, minus infinity to infinity or whatever the value taken by that random variable, if this integral is equal to 1, then we call this function f as a priority density function, or simply we refer it as a density function. Okay, so this is a definition. I'll be sharing this material, okay, the later in the due course. Okay. Yeah. Now coming to this one, the continuous distribution. There are many continuous distributions are there, and due to limitation in time and also whatever the constraint is there, I am going to discuss a very few standard one. Okay, which is quite uh, has a lot of applications. One distribution is uniform distribution, which is very basic one. So the density function is given by f of x is equal to 1 by theta 2 minus theta 1, where x lies between theta 1 to theta 2. If this theta 1 is equal to 0 and theta 2 is equal to 1, then we call this uniform distribution as a standard uniform, and it is denoted by capital U inside the bracket 0 comma 1. Okay, so in general, if any distribution means, in general the uniform distribution over theta 1 to theta 2 is defined with the probability mass function, probability density function given by f of x equal to 1 by theta 2 minus theta 1. Okay, where this theta 1 and theta 2 are any real values. In fact, they are called as a parameters also, and 0 otherwise. So coming to exponential distribution, as I told you, this has a lot of applications, especially in the case of lifetime data analysis. The PDF of exponential distribution is given by f of x is equal to theta into e to the power of minus theta x, where x is greater than 0 and theta is greater than 0. So this is a range for x, and also the value taken by the parameter is theta is greater than 0. Now in standard, in some books what they write is 1 by theta times e to the power of minus x by theta. So you can write in any of the representation. I have chosen this representation. Okay, any representation can be used. Okay, but provided whenever we talk of a distribution, we always talk of the mean of the distribution. In this case, exponential, the mean is going to be 1 by theta. I think many of you have come across this distribution in your courses. This is one of the standard distribution which we are going to discuss. Coming to the next one, the celebrated one is normal distribution. This is one of the heavily used, which has a lot of applications in real life situations. Hence, this is called as a celebrity distribution. So the density function is given by f of x is equal to 1 by root 2 pi. Sigma will be outside that root into e to the power of minus x minus mu whole square divided by 2 sigma square, where x takes the value on the real line and mu also takes the value on the real line, and sigma is going to be greater than 0. So what happens is, in many when I was taking classes for many the batches, some students or some audience, they have a habit of writing sigma square greater than 0 while writing the normal distribution. Actually, square of any number is already greater than 0, but it is meaningful to write always sigma is greater than 0. So here mu is called the location parameter and sigma is called the scale parameter. So in the tomorrow's session, when it comes to the testing part is considered, we are going to talk more on these parameter space, the value taken by those parameters, estimation and testing part. Okay. Right now, just look into what is the basic structure of a distribution. Discrete distribution means what? Continuous distribution means what? How to plot those distributions. Why do we need plotting? Because if you see the expression of these things, whatever is the f of x and all those things, immediately it is very hard to grasp that how these distributions are behaving with the collected data, or how the pattern of this function look. Hence, it is always a best practice to plot these functions and see how it is going to behave. Hence, always we go for plotting those distributions. Either it can be a discrete or it can be a continuous. Okay. So now we shall take one by one. We shall plot these distributions and we shall see how the pattern of this distribution looks. Okay. So shall we start in R?
Yes, sir.
Yeah. I understood in morning session already you are familiar with what we call. Some people are using R Studio and some people are using whatever the regular R is there, R console. Okay. So right now I am using R console. Okay. Is this font is fine? All of you can see. Is it readable or I have to increase the font?
Yes, sir.
Yes, sir. Readable.
Yeah, it's readable. Okay, fine. So just I have prepared some questions for this session. Okay, first of all, we shall go for sketching the graph and simulation of random numbers. Simulation of random numbers I will take to the next part. But before that, we shall, in another half an hour, we shall finish this sketching the graphs of this following distributions. So we shall take the first question.
Sir,
So
sorry to interrupt you. Can you please increase the font size in our console?
yeah, I will do it, madam. Once I
Yeah.
start, I will do it.
Okay, okay.
That's why.
Thank you.
If there is anything like that, please let me know. Okay, I will
Yeah,
do
yeah.
it. I will do it. First, let me understand the question, and then we shall go to that part. Yeah. So coming to this one, this is our task. Now we have to work on this. So we have to sketch the PMF of the binomial distribution. Okay. In the place of n, binomial distribution always has n and p. N is a number of trials, and p is a probability of success. So here we shall fix n. N is going to be 10. You can fix any number. Okay, maybe 20, 25, 30, depends on your interest. So in this, whatever the uh, example is considered, I am going to consider n is equal to 10. And p value, I have chosen three values. Why? Because is, if you look into this, I am sitting at 0.5 because p lies between 0 to 1. I am sitting at the center. I am going below 2 times and I am going above zero point 0.2 times. Okay, a zero point 0.2 I am adding. So this has one significance. When you come to this 0.5, if you look into the graph of it, I'll be talking more about this part. Okay, zero point 0.3 and zero point 0.7. Yes. So let us start the program now. Okay, and we shall see. So this is a program. Already I have typed this one. Okay. Just quickly you can open R and you can type this question. Okay. So first what we shall do is, instead of going all together, okay, with p equal to 0 0.3, 0 0.5, 0 0.7, that we can change once we write only for one particular case. That means we shall start with binomial 10 comma 0 0.3, and then we can change the program, the values in the program, and then we can go with the further things. Yes. So I'll be taking a script file. Okay. So yeah, just a minute. Okay. So remember here, I'm not going to use any inbuilt function initially, but once if I complete this program, then I'm going to show you how to use the inbuilt function also. Okay, there are inbuilt functions which are available in R, but only for the first case I'm using this program. It means directly how to write the codes for it. Then we can go with the inbuilt function. Okay. So first, what I have to do is, if you look into the PMF of the binomial distribution, it is probability of x is equal to ncx, means n choose x, p to the power of x 1 minus p to the power of n minus x. Here n is already fixed. N is going to be 10. Okay, let me increase this one, okay, so that it will be more visible. So n is fixed, that is 10. Only I have to vary p. So for that, what I will do is, initially I will take n is also some variable. Okay, so let me initialize n is going to be 10, or whatever value. If you want, you can change that one. So once we define this, initialize these values globally, whenever you need, you can change that one, or you can use scan function. Okay, so now we shall initialize p value also. We shall take initially 0.3. Now coming to this one, I have to compute the probability mass for, or PMF for this, or probability value, whatever is the probability of x is equal to small x. So let us take, because my x random variable will take 0, 1 up to n. So let us define a sequence for it. I think already you are familiar with the sequence function. I need 0, 1 up to n. So here there is only 10 values. I can simply type C of. I can just write C, open the bracket, 0, 1 up to 10 I can type. But if I don't know what is the upper limit, that is n value, if I don't know, you can use sequence function. Sequence of 0, comma, whatever n. So let me run this command. So first value is already taken. Then p is also there. So x. Now, so what happens is, if I have many lines in R, this is one of the best practice. So once if we get an error in any of the step, we can able to debug that error. So this is one of the practice which I use. Okay. So x values is already taken. So now x is a vector which has a values 0, 1 up to 10. Now for each of this value, whatever is there, 0, 1, 2, 3, on each of this value, I'm going to compute the probabilities. That is the mass, PMF, whatever the value is there. So for it, I will write the command. So let me take PMF, whatever is there. So NCX, okay, for NCX, there is a command called nChoose. Actually, it is nChoose X, which is in R we use this inbuilt function, that is nChoose X. Totally, what it does is, it will compute NCX for each value. So this is one of the advantage in R. Actually, if you look into the other programming languages, for each value of x means I have to define a for loop, and then I have to compute, I have to consider, I have to access each element in this vector. But in R, directly we can compute, we can what? We can make a computation on directly vectors, so that it will taken care whatever the elements are there in that vector. Okay. So this is one of the advantage in R. So next I have to take NC choose into. So I have to consider the p, whatever is there, p to the power of x into, I'll take 1 minus p to the power of n minus x. So if you want to be computed clearly, so you can put a bracket so that hierarchy will be taken over there. Anyway, this bracket is not needed now. So this is the entire command to compute the PMF in each of these values 0, 1, 2 and n, whatever is there. Okay, so let me run this command. So to run each of the line, the command is Control R. You can hold Control button and you can press R. But in the case of R Studio, it is different. Okay. Now look at this. It has computed all the probability masses. So let me print the mass. So if you observe on each of these, when x takes the value 0, this is a PMF, the value of the probability, whatever is there. Then this is also again. So it has taken care with all the 11 values, including 0 here. Okay. So once if you compute this one, then we can go for, as I told you, so we have computed this probability mass, but we don't know how the things are behaving. So to get a pleasant look of all these things, we can go for plotting the PMF. Usually what happens is, as I told you, this discrete means we are not going to get a continuous curve. On each of those values, whatever we have 0, we have this much is a mass. At 1, this is a mass. So we are going to get something like a line chart. So we have to specify that line chart. How to do that one? Just we can go with this. Okay. So there is a command called plot. So this plot will does plotting the whatever the values we are going to consider here. So whenever we go for plotting, that means it will give a graph in x-axis and y-axis. So we have to mention what is there in x and what is there in y. So here on x-axis we are going to consider these x values, and in the y-axis we are going to consider this whatever the probability mass is there. Okay, so that is, so this will simply give you the plot of this PMF. So moreover, whenever we wanted to mention the title for that graph and also what type of chart we require or what type of graph we require, we have to mention the remaining things. That will be done after this PMF. So there is a command called main. So this will help us to give the title for the plot. So this one you can simply say that plot of the PMF of binomial, whatever is there, that you can mention. Okay, 10 comma 0.3, close the bracket and close the inverted comma. So after this, we have to give what type of the thing we are going to get, that we can mention. Okay, so for that we shall use a command called type. Type means what type of graph we need. So we are going to use what we call the H for this. The type is going to be H and close the bracket. So in this plot command, what are the things we have mentioned? We have mentioned x, that is the values which occur in x-axis, and what should be in the y-axis, that is the PMF. Then we have named the plot as this, and then type equal to h. So now let us run this one and see what is the output. If I want to run the entire program, just select the entire thing and you can click on this run. So if you observe here, we have got a plot of the PMF, that is on the value 0 we have this much mass, on the value of 1 we have this much, 2 and so on. So once it goes above 8, automatically it is going to be very close to 0. Okay, so this is one of the plot, okay, for 0.3. Okay, so you just look into this plot. I'll be coming back to this one later on. Okay, So similarly, I will copy the same program. Okay, just I am changing the to separate this one. I will use this command. I can make this as a command. I will take the same one. I will make the change as 5. So if you look into the plot of this one, okay, we can observe most of the things are towards left. Most of the masses towards the left. After that 8, it is almost going to be decaying. Okay. Now coming to this point 5, if I run this program, if you observe the plot of this at 5, whatever is there, you will see some peakness, and below that and above that, okay, you can see the masses are going to be same on the either side. That is less than 5 and more than 5. Once if you have such kind of distribution, okay, we call that distribution as a symmetric distribution. I'll be talking more on this in the next session. Okay.
Good evening, sir. I would like to
Yes.
ask about one question.
Ah. Yes,
Sir,
please. Go ahead.
sir, how to generate sample for non-closed form CDF?
Yeah. Okay. Okay. Non-standard you are asking. Okay.
Non-closed form, because their
Non.
CDF is, for example, incomplete gamma function.
Okay. Okay.
CDF is non-closed.
CDF is non-closed. Okay. You're talking about the CDF. Okay.
Yeah,
Sir, actually there is a two techniques are there. One
yeah,
technique we call it as a accept reject method.
yeah.
That helps you for any distribution, even for a discrete distribution it helps. Accept reject method, and another is inverse transform method. There are two methods are there, and
But
that
there, sir,
method is
inverse is not exist. So suppose one continuous
yeah.
distribution, their
See,
inverse is.
inverse doesn't exist means you can go with the accept reject method. That will help us. Okay.
Can you explain,
Yeah,
sir, this method?
I will give you a reference. There is a
Okay,
book
okay.
by Sheldon Ross, Simulation.
Yeah,
The
okay,
title
sir.
of the book itself is Simulation.
Okay,
So
sir.
clearly, he has given the many examples to generate whatever you are telling. If it is not in a closed form, how to
Yeah.
generate the observations from that one.
Okay. Thank you, sir. Thank you very much.
Simulation. Title of the book is Simulation, and it is written by Sheldon Ross.
Okay. Thank you, sir. Thank you.
S.M. Ross. His full name is Sheldon M. Ross. That's one
Okay.
of the very beautiful book. If you go through, you will get all the techniques, how to generate the random numbers from discrete, continuous, and whatever the distributions you are telling. You will get all the material over there, complete.
Okay. Thank you, sir. Okay.
Yeah. Even you can write to me. I will just put my email ID later on. I have a
Yes, sir.
soft copy. I can share with you. Okay.
Yes, sir. Can you
Yeah,
your
yeah.
email ID?
I'll put my email ID at the end. Okay. In
Okay.
the comment box, I will put it, or else you
Yeah.
can get it
Okay.
from the madam also. Okay.
Yeah. Okay. Thank you,
I
sir.
have a book I can share, and we can discuss. Sure.
Okay. Thank you very much, sir. Okay, sir.
Okay. Yeah. So now coming to this part, this
Sir,
distribution. Yes.
so sorry to interrupt you. There are some questions in the chat box.
Okay.
Would you refer to those?
Okay. Okay. Just a minute. I'll go through. Okay. How to run statement in RGUI editor. Okay. Right now I'm not using any RGUI editor. I'm using this R Studio, and I'm using this R console. Okay. I will go through this one in tomorrow's session. I will tell you. Okay. Okay. Control yes. Vipra Sharma has written one comment. Control R. Okay. If you go to this console, I will just show you. Okay. Coming to this part, this n is equal to 10. You just hold on control, and if you press R, it is working. See here, it works. If you use the script file, this new script, if you go to new script and if you start typing, control plus R will work. Yes. One more comment. Just a minute. Okay, H is type stands for S. That's a height, whatever is there. It stands with this line graph, whatever is there. That's a type for line. Okay. Simply, if you don't mention this, whatever the things over there, if you don't mention the type, I will just show you what happens. By default, it will take the line graph. Actually, line means it will put a dot dot dot. Okay. So if you put type equal to L, it connects all these dots. Okay. Otherwise, it will simply give the dot. By default, this is a type which is used in R. So here, to get a better idea, we are using type equal to H. Any other comments? Okay. Okay. Fine. Histogram I will come at the end. Okay. Fine. Now, this is about the binomial. So I will leave to you for the exercise. You can check whatever p values are there. You can just look into how the graph will look. That you can go for a in your practice thing, whatever. But more, what I wanted to tell you about regarding this 0.5 is whenever you take a binomial distribution with p equal to half, that is 0.5, we are going to get a symmetric distribution. Symmetric distribution means whatever the masses on the either side, it's going to be equal. Okay, so here up below 5 and above 5 is at mean, whatever the things over there, it will come as equal probabilities. Okay, this is one of the thing which I wanted to highlight. Okay, 0.7 or whatever the values are there, if you take any value in between 0 to 1, okay, you'll get a different plots. You can see when it is right skewed and when it is left skewed. Okay. Okay, so this is about the binomial distribution. Now coming to the second one. So regarding the Poisson, we shall talk. Again, coming to this Poisson distribution, the PMF of Poisson distribution is already I have mentioned. Okay, so P of x is equal to this much, whatever is there, e to the power of minus lambda. This e is nothing but the exponential. Okay, minus lambda, lambda to the power of x divided by x factorial. Okay, where x takes the value 0, 1, 2, and so on. So this is up to, this is called the countable. Okay, whatever the things over there. This lambda is a parameter which we call it as a rate parameter. Okay, as I told you, it is used to model the rare events. So this lambda is nothing but the rate at which the events are going to occur. That lambda is referred as a parameter which is nothing but the rate parameter. We call it as a rate parameter. Okay, so now we shall see how to plot this one and see how the graph looks. Again, this is a discrete distribution. Okay. So the command is quite similar to that whatever we had earlier. So, but here one should know how much till what value I have to stop computing these masses, because x takes the value 0, 1, 2, and so on. Okay, but usually those who are having a experience, so they will see that after some stage the probabilities are going to become 0. Okay, that you can try in this R program. Okay, let us see with the those things. Okay. Again, here also we have to generate a sequence of observations. So first let us fix whatever the lambda is there. Okay. Okay. So first we shall fix the lambda. Let us name it as simply LMB. Okay. So to finish it off quickly, this discrete. So let us take lambda is equal to something like 3. Lambda is greater than 0. I can take any value. So whatever you like, you can assign that value and you can see that plot. Okay. So then I can use some name. So since it's a Poisson distribution, I will use this name for my reference. You can give your own name for this one. So again, you can type the entire function, or else you can use the inbuilt function. So I'll be typing the entire function, then I will show you how to use the inbuilt function. Okay. So here that is given by e to the power of minus lambda. So that means we have to give exp. So the function for the exponential here we are using it as exp. Okay. Exp with minus lmb, whatever the name you are given for the lambda, into next is going to be lambda to the power of x lmb to the power of x. That means x I have to define. I will define it. Okay. Divided by, so this entire thing whatever is said, this comes to the numerator. Be careful while typing the program. So if you miss any bracket, you're going to get an error. Again, you have to trace that one. It is very difficult. So always make a practice. First, once you open the bracket, immediately close it. Once if you try to close here, you open a bracket wherever it is required. Okay. Divided by, so I have to compute x factorial. So the command for that one is factorial. Inbuilt function what is available in R is factorial of x. Again, I told you the advantage of R program is even the computation can be made on the entire vector. It will take about the component wise, whatever is there, it access and it will do it by itself. So now I have to define what is x. So again, x is equal to sequence of 0 comma. Now I have to go to certain limit. Okay. So let me consider that limit is equal to something like 20, and we shall see, because after certain point we are going to get the mass is equal to 0 here. Okay. So this is a command now. Only in 3 lines we have written. So let us run this one, Control R, and see if I am not getting any error. Yes, I am not getting any error. So directly I can go for the plot command. Okay. So again here also we are going to plot the PMF. Plot x comma. So whatever the name we have given, voice PMF. Again I will use type equal to h. And if you want, you can give the name. Main is equal to PMF of horizontal distribution with parameter value you can give. Another key layer we can laptop. Either. Okay. So this is about boson distribution. So we are giving this and this one. So let me run this one. So now you can see the PMF of boson means after 11 or 12 or 13, almost when it comes to 20, it is going to be very close to 0. Okay. So even you can increase whatever the values are there, even you can go to up to 30 also. Okay. So that's why the software will make very simple, the complicated things very simple. If you want to plot it on a graph sheet, we know how much difficult it is. But since the software is there, you can increase to any values. Okay.
So the plot, that's what I was saying. Okay.
Yeah, plot here. Yes, I'm showing the plot. Since I have changed it to 30, yeah, it will come. Okay. Okay. So you can look into the plot of boson. You can take different values for the lambda and you can plot yourself and you can get convinced how the graph will look. Okay. So this is about the boson distribution. And next one is the geometric. Okay. Again, for the geometric,
So Miss Dharya has a question, I guess. She's
Okay.
raising her.
Yes. Yes. If you have any question, you can ask me. You can unmute and you can ask.
Dharya, you have some questions? Dharya Tripathi.
Either
Okay.
she can put it
You
in
will
the
talk
chat box, madam. We will go ahead. Okay.
Okay,
Yeah.
yeah. Okay.
Okay. So now geometric distribution, again I told you, only thing what you can do in this R is whatever we have computed here, this mass, we can change the function. So if you look into the binomial case and in the Poisson case, we have changed the function. That's all. Remaining things will be as usual. Okay. Even in the case of geometric, again, we are going to have x takes the value 0, 1, 2, and so on. Okay, it depends what's the PMF, the form you are considering. Okay. So if you look into the geometric distribution, again in 3, 4 lines we can get that one. So that is going to be p into 1 minus p to the power of x. Whatever is there, so this will come similar. Only here we have to change. It is nothing but p into 1 minus p to the power of x. I'll close this one for a minute. Now I have to define what is p. So p is, if you look into the range for p, in the case of geometric, it is going to be 0 less than p less than or equal to 1. So here I will take 0.3 only anyway. So now I can run this program. So there is no error in my console. So this is how the, actually it has become Poisson. So we can change it to geometric. Geometric with, you can take 0.3. Even you can take this as a geo. You can change the names wherever required. Now we have got a PMF of geometric with parameter value 0.3, and this is how the graph will look. Okay, so this is about how to plot the PMF using R. Okay, so quickly I will talk about exponential, normal, and then I will talk about the inbuilt functions which are available in R. Okay, so now we shall go to the continuous case. In the case of continuous, I don't know, in the morning session you have done plotting the functions or like that. Anyway, I'm going to tell you how to plot any given function. If it is a continuous function, the things are different. If it is a discrete, you know how to do this one. But when it comes to the continuous function, the x values, whatever you are going to consider, it will be on the interval. And to get a plot, to get a continuous curve or a curve, whatever the things over there, we have to consider x values as, we have to tune the values of x as fine as possible so that we will get a better thing. Okay, so first let us go with the exponential thing.
Sir,
First,
there's a question in
yes.
the chat box regarding geometric distribution.
So geometric plot once again. Okay, yeah, the plot is here. I will be showing. So this is a plot. You can observe there is a decay, exponential decay we call. That's why I told you this is a discrete version of what we are going to consider the exponential distribution. Okay, there is a, clearly you can observe there is a decay, exponential decay here. Okay, I hope I have answered for your question. Okay, fine. Yeah. So now coming to the exponential distribution, first we shall talk about the uniform. Means it's a rectangular distribution that I will be talking in another 2 minutes after this. First we shall go with the exponential distribution. So when you come to exponential distribution, the PDF is f of x is equal to theta into u to the power of minus theta x. X is greater than 0. Now look at this. X takes a value which is greater than 0. So hence I cannot use the sequence by 0 comma whatever the specified number is there. I have to make an increment here. So when I start with 0 onwards I have to take the x values as fine as possible. Fine means as less as possible. By default in R, whatever the sequence function we have used here, by default it will take an increment of 1. Means it will generate a sequence of observation from 0 to 30 with increment from each observation 1. It will take it as 0, 1, 2 and so on. But here we don't want like that. You can use that, you will get the answer, but sometimes it is not going to be advisable to use like that, because you should know more of the things. Now we shall generate, sorry, theta I will take it as something like 2. Okay, theta is greater than 0. If theta is equal to 1, we call it as a standard exponential. Okay. In the exponential distribution, theta equal to 1, it is called standard exponential. We shall take theta equal to 2 here. Okay. Then we shall generate this sequence of observations, that is x. That is, we are going to have something like 0 to it almost 4 or 5 it will come to 0. That is already we know since we have plotted that one. But for your understanding purpose, you can start with any number and later on you can consider that one. Okay. Okay. So now let us consider this to be something like 10. You can take as many as possible, because in software we can get it in one stroke. Now we are going to use command called, we are going to add one more thing to this sequence by 0.05. That means now we are defining how much increment we want. Okay, it starts with 0, next it will take 0.05, next it will take 0.1, like that it keep on increasing till 50 with the increment in each step by 0.05. Okay, now we shall compute EXP, that is EPDF. Yes. So we shall compute the PDF for this, means the value of the function in each of these x values. Okay. So that is going to be theta into theta means I have called it as THE into, so it is going to be EXP of minus THE into x. So I have opened the bracket here. Okay. Hence I have closed it at the end. So again here. So whenever you work in R, be careful about the brackets. Okay. Yeah. After this, again we are going to plot this one. Okay. Again take same. Now here we are going to plot the value of the function at each x. Okay. So that is EPDF. Okay, I will use main is equal to, I will call this as PDF of exponential. It is denoted by EXP of, so I have taken it as a 2. So let me close this. Yeah. So earlier case I have used type thing. Here I am not going to use any type, because if we don't mention this type, we are going to get with the whatever the bubbles are there. Okay. So let me run this whatever the commands are there. Now if you look into the plot of this, you will see the bubbles will come. Okay, and clearly this shows if there is an exponential decay again. So this is a continuous version of whatever we have seen in the case of geometry. Okay. Now coming to this one, if I don't wanted this bubbles to be there, instead of it I want a line. So then I can mention the type, whatever whichever type I want. So to get a line graph, sorry, the line, whatever the things over there, joining all the points, you can use L. Type is equal to L. So if you use type is equal to L, we are going to get a smooth curve. Okay. So next you can change with the different things. Okay. If I take theta equal to 1, let me see what happens to this one. If you look into the graph of 2, it starts from 2. Okay. But if you start with 1, this is called the standard exponential. Okay. It has to start with 1 and it has to decay. Yes. If you look into the graph, it starts with 1 and it will decrease. Okay. So this is the advantage of plotting the graph, okay, of the PMF or PDF. Means we are able to see how the plots are, or how the functions are behaving actually. Okay. So this is one of the thing which I wanted to show you. Okay. Next I will show about the normal distribution, and then uniform we can just type whatever the function is. Okay. If you keep on changing this function, it works. Okay. That I'll be, as I told you, I'll be providing a write-up of completely whatever I'm going to do now. So there I am going to mention the commands and all the things. The output also will be there. That madam is going to circulate to you once if I provide to her. Okay. So now coming to the normal, this is one of the very important one. Okay. Uh, to understand how the normal distribution behaves. Okay. As I told you, if you look into the PDF of the normal distribution, okay, let me show you the PDF. If you look into the PDF of normal, there are two parameters involved. One is mu, which we call it as a location parameter, and another is a scale parameter sigma. I have to define. If this mu equal to 0 and sigma equal to 1, we call that distribution as a standard normal distribution. Okay, mu equal to 0 and sigma equal to 1. Now let us see how that mu equal to 0, sigma equal to 1 looks. Again here also okay, but here if you look into the values taken by axis over the entire real line, okay, and one of the property of normal distribution is it is a symmetric distribution. Means whatever you observe, okay, on the left hand side below the average, that is mu, and above the average, that is mu, you will see the pattern both are going to be same. It's a symmetric distribution. That too, if you take a standard normal, that is mu is equal to 0 and sigma equal to 1. So now let me define what is mu. Mu is equal to 0 and sigma means yes, G I will, so I'll simply abbreviate it. I can type yes also. There is nothing wrong. So we shall consider it as 0 and 1. So here you cannot start with the 0 because this is over the entire real line. So what I will do is I will consider minus 5 as a initial point and I will go up to 5. Okay. Increment you can take it as same by equal to this. So now I will use npdf, whatever the things over there, and I will type the entire command for that one. Okay. So what is the command for it? So it is 1 by half 2, that is 1 by square root of 2 pi. Okay. So the command for it is square root of 2 into 2 into pi. That is the command for pi is pi into we have sigma, that is sg, me close the bracket for this. Again, I have to close one more because that is corresponds to the first term. Then comes exponential, that is e to the power of x into, let me complete the numerator in that exponential, whatever is there, that is minus times. We have x minus mu the whole square divided by, again I have 2 times sigma square. So that sigma square I can put to the power of 2, or simply I can type twice. Okay, I have to close, I have to be very much careful about the brackets. Let me run only up to this point, and plot we can go later on. There is an error. Okay, SQ. I think I have used SQ in this. That is SG.
Sir, we have to define pi.
Huh? Yes.
Sir, do we have to define the value of pi?
No. In R, this is an inbuilt. It will take whatever the pi value is there. If you mention pi, it is already predefined. Okay. No need to define pi. Pi is already defined in the R. It's a standard one.
Okay, sir.
Okay.
Okay.
So now there is no error regarding this, whatever we have. We have computed the PDF. So now let me consider this as NPDF, PDF of normal. So it is written as normal 0, 1. That is our standard normal. So if I run this command, so if you observe the plot of this, clearly it is a symmetric distribution, symmetric about 0. Now let me keep this sigma as same, but if I make a change in mu, then let me see how that graph will look. Okay. So clearly in this graph, if you see, it is symmetric about 0. Okay, if I take mu equal to 1 and sigma, I will retain it as 1 only. So if you observe the plot of this one, whatever mu 1, clearly you can see this graph is going to be again symmetric about 1. That means there is only a shift. The curve looks very similar to whatever you have seen in the earlier case, but only the thing is the graph is shifted. Okay, the symmetric graph, whatever is there, it is shifted from 0 to symmetric about 1. Okay. Yes, you can observe that one. So now clearly to see both the graphs in one plot, okay, what you can do is, so you can compute one more time. So this is equal to mu 1. Okay, so what I will do is mu 1, I will keep it as 0 and 1, whatever the earlier graph is considered. So wherever mu is there, I will change it to mu 1. Okay, so this I will call it as a NPDF1. Again, I will compute with the different value of mu, but sigma I will keep it as same. Okay. So this I will call it as a mu2. Means I will compute both mu1 and mu2 for these values, whatever the PDF is there. Okay. I have taken both 0 and 1 for the mu. Sigma I have retained same. If you want, you can define sigma 1, sigma 2, and you can also change that. Okay, that depends on your interest. So now here I am computing the PMF for both the values. Okay, and I am going to add both the graphs in one plot, both the lines. So for that, the command is, the first one is plot. That is by default you have to define that one and you have to plot those things. Okay, simply I will put it as a normal curves. So to add the other graph for the same one, other lines, we can use the command called lines. This is one of the command which we use. Again, you take X and you take npdf2. Again, here also it is npdf1. Okay. So let me check this one. So there is no error. I have run this program just by adding this npdf2, whatever the things over there. Just I have considered two values for the mu1, mu2. Now looking into the graph, look at this, corresponding to this one, whatever is there. Okay. So this is about 0. This is the first graph. Whatever you can see here. This is the second graph. Means there is a location shift. The same graph is just shifted to having a center value 1. So you can add as many lines if you want for this, for different values of mu, and you can see how the location shift is happening in normal distribution. Also, here I have given type equal to L. There are different other things are there. You can add colors for it, and you can give different colors for this one. So that you can see in any of the standard R book. Okay, when you go for the plots, still there are more functions and more things can be applied for it. So that part I will leave to you. Okay. It's a spelling mistake. Okay. So this is all about the normal distribution. Okay. So this is what just I have covered. In the case of discrete, coming to the continuous distributions. Okay. So here, if you observe all these programs, whatever we have written, we have not used any inbuilt functions regarding the distributions. Okay, we have used like choose or whatever the other things over there, that is fine. But considering any of the distribution, we have not used any inbuilt functions. There are some functions which are available for standard distributions. To use those commands, just I will give an introduction about a binomial. Then any other distribution you can use with the similar one, whatever the prefix is there. Okay. So the inbuilt function to use binomial distribution is as follows. Okay. Just quickly, I have another 10 minutes. Okay. I will finish this and I will just talk about one of the fitting of distribution concept. Okay. So now coming to the inbuilt function, whatever is there. So there are 4 things available for all the distribution. One is D, P, Q and R. What this D, P, Q and R will tells us, let us see one by one. Okay.
Sir, sorry to interrupt you. There is a question in the chat box.
Yes, yes. Type equal to L. No, it won't. It has to work. Just check, have you typed L or 1? Because both looks very similar. There is no difference at all. See, this is 1, but this is L. Type L for it. Okay. Just check. Fine. Okay. Okay, that's fine. No need to ask any apology. Whatever is there, the doubt you can ask. Okay. Now coming to this one, these 4 things are available for all the distributions. There are some standard syntax is there for each of the distribution. One that is D binom. What this D binom will do is it will compute the probabilities. Whatever the mass we have done, that will be done with this D binom. Now just quickly I will show you how that will work. Okay. So now coming to this first part, I'm not going to plot. Look at the PMF. Now coming to this R console, whatever is there, if I type PMF, I'm getting all the 10 values. So here I have not used any inbuilt function because I have typed the function entire, whatever the PMF is there. There is a standard command, that is what I am telling you. There is an inbuilt function called dbinom. So the command is dbinom of this k is nothing but the x values. You have to plug x values, or you can specify some value also. If you want some particular PMF at particular value, that also you can mention. N is the number of trial and P is the probability of success. Now we shall use this inbuilt function. Okay, I will be typing that one in R console only because you can see the thing which is going on. So there is d binom, and you have to pass the arguments for this function is I will take x means all values. Then I am going to use n is equal to 10 and p equal to how much I have taken here. Let me see. P equal to 0.3. So I will type 0.3 here. So this is a standard command. So if you see this one, so whatever we have done using this entire thing, that will be done with the inbuilt function also like this. Even in particular, so if you press the upper arrow key, you are going to get X. Even you can see what happens at 0 also, particular value. You are going to get the same. Okay. So similarly for the other distributions, there are command like that. Like d binom, you have d poise for the Poisson distribution POIS. Okay, and for the geometric you have GEOM. Okay, and for normal you have d norm NORM. Exponential you have DEXP. So these are some of the commands which are available. If you go through any standard R manual, you will get all the commands for each individual distribution. This is what this D binom will do it. Okay. Now coming to the P binom. So P binom means I have not told about the CDF, cumulative distribution function. So if you want to compute the cumulative distribution function for this, you can use P binom or P norm for a normal, P unif for a uniform distribution. Okay, you can get the cumulative distribution function for that. So again, this is going to be 10, comma, whatever, 0.3. Look at this. What it does is, it will cumulate these probabilities. First value will remain same. Then first one and second one will be added. Both putting together, you are going to get in the second position. Then for this second position, the third will be added and it will be displayed here like that. So that ultimately you are going to get 1 at the end. Okay, because that will give you sum of all the probabilities. So this, the function of this P binom is it will compute the CDF. So similarly, we can go for what we call the Q. Q means that is a quantile function, Q binom. So remember here, for the Q binom, the command is you cannot pass X values, you have to pass the probability. That is what the inverse will does. That quantile function, you have to pass the probability. So I will compute something like 0.02. Especially for continuous, it is very easy. You can make a practice of that. Q binom. You can put some value, whatever, 0.3 n, 0.3. So it will give you the quantile. So the quantile is 2 here. Okay, because if you see this 0.3, if you observe this CDF, so it will be in between this to this. Hence it will take the upper limit as 2. So if you want more than one value, at 0.3 you have computed. Suppose if you want a quantile value for the more than one values, so you can pass the vector also. Okay. But remember, it should be a probability. It will be in between 0 to 1. So I will take it as 0.5. I will close it so that I will get the two values here, 2 and 3. Even if you take it as 0.9, the second value, you are going to get 2 and 5, like that. Okay, so this is about the quantile function which we are going to use. And the last one is very important one is R binom. R binom is nothing but the random variables or a random observations we are going to generate from a specified one. Okay, this R stands for random numbers. So this whatever small n is there here, the small n is how many observations you have to generate or you want. Okay, so the first one in this argument is how many observations I have to generate. Suppose if I want to generate 5 observations from the same distribution, that is n is equal to 10 and p is equal to 0.3, I will get 5 observations from it. Okay, so from binomial with n is equal to 10, p equal to 0.5, means it will take the value 0, 1 up to 10. In that, I am going to generate a random sample of size 5. That is, first observation is 3, second also 3, third also 3, fourth is 4, and fifth is 5. So if I run the command again, now my sample will change. So each time whenever you run, whatever the number of samples you are going to generate, the samples are going to change. So you can generate as many possible observations if you want for what. So this is called the simulation thing that we are going to do it. Whatever the methods or whatever the proposed things are there to validate that one, because getting real-time data is itself is a very much difficult, which involves a lot of time and cost. Okay, sometimes to validate whatever the things that we have proposed or we have developed, we make use of random numbers from any specified distribution, which can be done using this inbuilt function. Okay. Also, if you don't want to use this inbuilt function, as one of our friend asked about any other function, if I know, I can use accept reject method or whatever the inverse transform technique is there. Okay, those two techniques can be used, and there are many standard books which have given the algorithm for that one. You can write your own program and you can generate the observations. Okay, so here I am using only for binomial distribution. Let me explain about one continuous distribution. I'll be considering exponential distribution. Let me take REXP. REXP, suppose if I want to generate 10 observations with parameter value 2. So the argument for this function is only 2. First one always stands for number of observations, and second one will be the parameters, whatever the thing. If you take normal, you have to pass two things, that is mean mu and variance sigma square. Exponential only one is there, theta. I have taken theta value to be 2. So I'm going to get 10 observations from exponential distribution. Okay. So these are all some of the things. Quickly, I will take another 2 minutes and I will finish one important test, or else I will talk about that one in the tomorrow session. Anyway, we have a non-parametric test only. So there is one test which I wanted to talk about. Okay, just I will give you an idea. There is a test called Kolmogorov-Smirnov test. Means whenever we have a data, okay, we have a raw data. That means the data is collected from an experiment. We have to see which distribution it follows. Okay, if I know discrete, I will assume some discrete distribution and I will check whether my data follows some specified distribution, or else if it is a continuous, yes, that is also fine. Okay, we have two tests for fitting of distribution. One is a chi-square goodness of fit test, and second one is Kolmogorov-Smirnov test. Chi-square goodness of fit test, we can use it for discrete, continuous, both the things. And for the continuous case, always it is most powerful when we use Kolmogorov-Smirnov test. There are many tests developed in literature. I'm not going to list out all those things. Anderson-Darling test is there. Then comes the other one Mrs. Thing is there. There are many other tests. I'm not going to discuss. I'm not going to talk all those things. But most widely used for the continuous distribution, to examine whether the data follows some specified distribution or not, we are going to make use of this Kolmogorov-Smirnov test. and the command is ks.test. I will talk more on this in the tomorrow's session. Okay. So
Sir,
with this, I
okay.
thank you all. If you have any doubt or anything, most welcome.
Sir, there are some questions in the chat box regarding
Yes.
the Q binom and sample
Okay. Okay.
replacement. Yes.
Okay. Okay. Yeah, regarding percentile, I have not discussed anything. Yes, if you want to generate with without replacement, there are different commands are there. Okay, in the write up, I will be providing all those things. I will make note of that one. Just a minute. With replacement and without replacement. Yes. Okay. Yes. Is there any limit for number of observations? No, there is no such kind of limit. Okay, but what happens is if you use, if your sample size, whatever the samples you are generating, if it is going to be very large, sometimes this program may get hanged. Okay, it has some limitations, but for the large value, okay, very large value, very huge. Yeah, in most of the cases what happens is we are going to study the sample size. Either we take a small sample, something like 5 to 10, a moderate one, which always we, this is not a standard rule, but it's a thumb rule. If the sample size is 10 to 25, we call that as a moderate. Below anything 10, we call it as a small sample. More than 25, we call that as a large sample. Okay, more than 30. In many books, they write more than 30. That's not a, there is no such kind of thing. What happens is, if you use more than 30, you can go for a approximating with a center limit theorem, most of the thing. But one thing what people will do is, as you rightly asked a question, what they try to do is, whatever the method is there, they generate some sample size, say n is equal to 30, and they repeat this experiment for 1 lakh or 2 lakh times. Okay, means each time they generate a sample of 30 and they compute whatever the things they needed, they go for repeating. Okay, that's what simulation we are going to do. That's called the Monte Carlo simulation. Yes. If not percentile, then what are the values we are getting after using q binom? Q binom is only quantile we are getting. Okay. But 2 and 5 represents those values. Okay. We are mentioned the probabilities. Let me show that one. Yeah, you're asking about this question, right? So these are the probabilities. Means, as I told you, if you look into the graph of this, I don't know. I think I have taken wrong. This is a PMF. If you plot the CDF, okay, that will be a step function, okay, which will be lying between 0 to 1. Always, I have not shown about the distribution function. If you plot the distribution function, you are going to get a step function, and on each of that, whatever the probability is there, its corresponding inverse you are going to get. That will be the quantile function. Okay, this quantile will be at sitting at this probabilities, whatever is there. If you take its inverse image, that will be the value. Okay, this 2 and 5 is that. Yeah, any other questions? Let me see. Okay. Okay, this Umar Thakur, right? Yeah, don't worry, no need to take any screenshot now. I'll be sharing my presentation as well as a write-up, whatever the notes is there. That I'm going to send to madam in a couple of days. Okay, madam is going to circulate to all the participants who are present here. Okay, you can use it for for a quick reference. Yeah, sure. Okay, thank you, Santosh Kumar. Yes. Yes. Anybody else? If you have any doubt, you're most welcome. Okay. Then, madam, we can stop the session.
Sir, would you suggest a beginner book for ours?
Okay.
Since we
Yeah.
are all beginners in this
Yes.
aspect, would you
Yes. I
suggest a
told
book?
about my email ID. Just a minute. I'll be putting my email address in the chat box. You can just write to me. I have some material regarding R. I can send to you. Those who want, you can just write a mail to me. I will share with you. Okay. Beginner, right from the scratch. Introduction to all the things. Sure. Make note of my email ID, raghunamm@gmail.com. You can write to me. I will send a material to you. Yes. Okay.
Any other queries from the participants? Okay, I think he's getting confused with this one digit after the decimal, 0.3.
Okay.
So can you just elaborate this so that?
Yeah. Okay. Just a minute. I'll just plot one graph and I will tell you how exactly it works. Okay. So usually what happens is, if you consider the discrete distribution, I am talking about discrete, even continuous also holds with the same thing. Okay. So what happens is, when you plot any CDF, okay, it will start with 0. CDF means cumulative distribution function. Okay. So there are different values, right? It will take 1, it will take 2, and so on. Usually what happens is, for the binomial case itself, if you take any value, so it will be a step function like this. Okay. Sorry, this is whatever n is there. So there are different values here. So it will be up to 1, 0 to 1. At last it will go to 1 and it remains 1 only. Now what happens is, there will be a jump. We call this as a jump. Okay. So again, once it reaches 1, there will be a jump which will go like this. Okay. From 0 to 1, it remains like this. And immediately when it reaches to 1, there will be a jump. This will go up to 2. I'm not plotting exactly. If you see the definition of this. So now what you are trying to see is, we are giving a some sort of probability. Okay. Say for example, this is 0.3. At 0.3, you see what is a mass. Okay. So what happens is, throughout this, whatever the things you see, from here to here there is a jump, but all of a suddenly it will go to this part. Now you take its inverse. Okay, this is what happens. So here this 0.3 is in between 1 to 2, whatever the things is there. So it will take this 2 as a quantile. Now coming to the continuous case, in the case of exponential, just a normal, whatever the things are there. In continuous it is very clear, but in discrete sometimes it may mislead. In continuous case what happens is, since normal distribution is always from minus infinity to plus infinity, so till some point it will be 0, and there will be a function like this, where this function is always in between 0 to 1. So the CDF is always in between 0 to 1. Now you want at some particular value, say something like 0.4. What happens is, you come to this, see what is the value is here, 0.4. Its corresponding x value. This will be your quantile. Even if you take something like 0.9 here, then what happens is, you go to 0.9, you draw a line like this, again you draw the vertical line. Whatever the value you are going to get, this will be your quantile. Okay, it's the inverse image actually. Okay, in between 0 to 1. Hence, in the Q function, we are going to pass the probability initially. Okay, not x values.